I wanted to speak a little bit today about the idea for scaled sprites using 74 series 5-volt TTL logic. So this idea came about from a short conversation where older retro-style arcade hardware was being discussed. And actually I came to the realization that scaled sprite display may not use as much logic as I thought. So without any rotation and just X or Y scaling, we actually just need to have one or two scale factors, perhaps for the X and Y, which I chose to have independent scale factors. And these scale factors can be multiplied by an accuracy value. In this case, I multiplied by 32, which is shifting the byte left 5 binary places. This gives us enough good accuracy where we can have scale up and scale down for sprites and not having too much complex logic. So I began by actually starting in the emulation code this time. I did not want to start with the TTL side until I was sure that the logic was actually quite or relatively simple. So I started by specifying, using the BDD 6502 framework, I started by specifying some what I thought would be good sprite register formats. Now this wasn't how it started. Some of the registers were in different ordering, and actually the ordering for this comes about because the sprite registers need to be stored into RAM, but the underlying logic needs to be progressive and actually read these different register values at different points. So actually I needed to have, say for example, I needed to have the MSB X and Y bits read early on, and I needed to have the Y position and the Y size in terms of pixels read early on. That's because the logic can actually do some early rejection based on the Y position and Y size of the scaled sprite. If it finds out that the scaled sprite doesn't need to get rendered at that particular screen position, then it actually early outs and aborts the current sprite, so it won't even read the X position, the X scale extent, the Y and X inverse scale values, and the Sprite Frame will just optimize the whole process and skip ahead to the next sprite. So I came up with some data that I might want to use, and actually I reused some of the existing data from some of the other previous hardware attempts, and I started to spec out the kind of logic that I wanted to see in the TTL, but I spec'd it out in terms of Java. But for every single pixel in the display, we have the display H and V and whether or not it's H-sync or V-sync. Now, all of these signals are readily available within the real hardware. And basically, I just started by using a similar kind of logic that was found in the original sprites layer, where I have the notion of two sprite Scanline RAMs. While one is being displayed and cleared from the calculated pixel values, the other one is actually having the calculated sprite values stored into the relevant position in the sprite Scanline RAM, so that for every horizontal pixel in the active display, it marches across the sprite Scanline RAM and then outputs the final pixel here, but it also then clears the pixel ready for when the sprite Scanline RAMs alternate over or switch over, and then what was being displayed then accepts calculated data and vice versa. This is actually a relatively simple part of the logic. The actual difficult part of the logic was handling the sprite schedule, and I'll go into that in more detail. But basically, the sprite scanline in this version is actually 512 bytes long. because we have a maximum horizontal resolution of 384 pixels according to the screen schedule and timing, then actually only the first 384 entries are really properly used within the Sprite Scanline RAM, but having it wide at 512 bytes meant that I didn't have to invest too much time in horizontally clipping the sprite data or horizontally rejecting the sprite data as I was calculating into the Sprite Scanline RAMs. And all of this logic actually starts on the positive edge of H-sync with an approximate value of 2 pixel line delay, or 1 pixel rather. And this H-sync edge is also readily available and triggerable inside the real hardware, so that's why I chose H-sync. I also chose the positive edge of H-sync because if I want to implement some kind of horizontal overscan mode at some particular point in time, then this logic layer wouldn't need to be re-engineered to trigger on a different point through the scanline cycle. I can just start on the positive edge of H-sync and everything will look nice regardless. Some of the other layers start displaying or start calculating the new scanline 8 pixels after the end of the visible data from the previous scan, which means that those other the characters, the tiles, the old sprites method would need a little bit of re-engineering to start triggering their calculation on the positive edge of H-sync instead. Anyway, so the sprite schedule handling is actually where the more complex logic starts to come in. So what I started with was that I have a drawing sprite state. Now this can be an internal counter, which it is inside the real hardware. But basically this sprite state starts off with 0, goes to 1, to 2, to 3, to 4. Now states 0, 2, 4, 6, 8, 10, 12, and 14 are all empty because I wanted to have time to set up the RAM address RAM address registers for the read, and then I wanted to have time on the next pixel clock cycle to then actually latch the value into some internal registers so that I can spread out all of the memory reads for fetching all of the different sprite definitions as they're stored consecutively in memory. So it will try and render this one, or it will early reject it, and then it will hop onto this one, for example, hop onto the next one. Here, actually, inside the test definition here, I've got several different sprite definitions laid out in memory. And if I run this emulation so you can actually see the kind of display that we're actually talking about and targeting, then what we have here is that we've got a couple of different sprite definitions. This one is scaled. This one is scaled down, this one is scaled up. This one here on the left-hand side here is a scaled up version of this sprite. This sprite, I've got a special rendering mode where I've flipped the quadrants over in the horizontal and vertical axis so that I can render the sprite data at different points. This one up here in the top left is flipped horizontally. All of these different sprites are here to basically test the different flipping mechanisms and different culling mechanisms. And also there's a transparency test here in the bottom right hand corner where the vertically flipped Turrican sprite is displaying over the Thunderblade building top, so that I can check that all of the masking and prioritization logic works within the emulation. So this is what we're actually trying to target. So if I go back to here now, we can see that it's beginning to read the current sprite part, incrementing the state. The current sprite Y from the sprite Y internal memory, and actually the sprite Y, because it has a single bit for the most significant bit for the Y, it orders it in at that point. So current sprite Y could be say for example, an internal batch triggered on the positive edge of the state advancing, and of course then it starts to, in Java, of course it's doing an invert because the Y position is inverted so that I can actually do an add and then do an extend check, much like the original Sprite hardware was doing. And of course it's doing an AND with one FF to basically simulate the fact that we want to be working on 9-bit values. In the hardware, this is all free because it's just selecting signals for the Y position. For example, the current sprite size Y in pixels is red on the next state transition, and then the state transition after that does an addition, which is in effect an addition with the inverted Y, which is a subtraction, and it does an inside height check. This is the early out check, so that if it's not actually needing to render the sprite at this particular Y position, then it skips over and advances to the next sprite. Otherwise, it will read the current sprite X and latch it. Again, in hardware, this would be a latch, and so on and so forth. And it's reading the sprite scale extent X. Then it's reading the inverse values, and of course the inverse values, when they are red, then it can start calculating in this particular point in the state the current sprite data Y pixel. The comment here says that it could be using a lookup table, which actually it does in the final hardware. It does a lookup table for all of this calculation. So it takes the initial value, it starts the initial value here, it adds it all in and everything else like that. And then it reads the X inverse. It starts off the internal pixel halfway into the first pixel that it wants to encounter with the half of the scale in inverted scale, so on and so forth, or inverse scale. And then lastly it reads the sprite frame. The last state that it goes into, the state does not advance from state 16. It sticks in state 16. And basically it goes from reading and latching the sprite registers to stamping sprite pixels out into the scan line at the particular X coordinate for the Y position in the screen that it's currently read. So what it does is that in Java, of course, it's got a whole bunch of shifting and bitwise ANDing. In hardware, this is just simple signal selection, and there's no need for any ANDing or anything like that. Again, in hardware, this actually detects horizontal and vertical flipping. In hardware, this is a couple of bitwise XORs. Again, much simpler in hardware than actually compared to the Java code. So what we have here is that this is actually the coordinate range check as well. So if the two top bits of the sprite frame are set for X or Y, it starts rendering a different quadrant of the sprite. It's just basically a free effect that I can use to render the sprites differently if I wanted to. If I wanted to lay out the sprite data differently, or if I wanted to have a different tiling for the sprite data, I can use the hardware and use this virtually free feature. And again, bitwise clamping is free in hardware because it's just signal selection. I don't need to do this kind of stuff in hardware because it just naturally selects the right signals. It doesn't have any concept of overflow or anything like that. The pixel color is fetched from the relevant internal RAM. Again, so we are using 16 bits per pixel. Sorry, not 16. We're using 4 bits per pixel, which means that per byte we can have 2 pixels. So I chose in the hardware design that the lower 4 bits or the upper 4 bits, the lower or upper nibble, will be selected based on even or odd sprite frame. So in Java, it's a shift. In the hardware, it will just be a signal selection. The color is used, again, handing out the color value with bitwise 0x, 0f. Is again just simple signal selection. There's no real ANDing involved in the hardware. And then eventually the sprite Scanline Ram, if it's cleared, if the sprite Scanline Ram has a cleared value in it already, in other words, pixel value is 0, then it stamps in whatever the sprite data is fetched from the sprite rams. And that's just basically a very simple piece of logic. The last thing it does is that it advances the current pixel being rendered in the sprite Scanline Ram by 1 pixel. And of course, the internal coordinate is updated with the inverse scale value, which is multiplied by 32, or shifted left 5 bits, so that actually this sprite x pixel value is a coordinate with more bitwise accuracy. And the final test, which again is quite simple and cheap in hardware, is to take the value but without the 5 bits of accuracy and compare it with the sprite scale extent x. Now, if it meets the criteria, if it's greater than or equal to the sprite scale extent x value, then it will reset the internal state and logic. It will advance the sprite, which advances the sprite index. It sets the sprite state back to 0, and then it reads the next sprite in memory, and it reads the next sprite in memory after that. And this logic was relatively simple to spec out in Java, and then I got something which looked a lot like this. And then I knew that I could then start to implement this in TTL, which is where we get to here. Now, this first sheet here comprises the Sprite Ram Logic, which exists up here in the top left-hand corner. So if I zoom in a little bit and then scroll around, you can see that there's some address selection logic here. It either uses the address, which is coming from the external address bus, which is when I'm wanting to write values to the Sprite Ram, which is here, or if it's not writing values to the Sprite Ram, then it uses the address, which is calculated for the current sprite state using the first few low bits here for the sprite state, plus the sprite index that we want to read. So doing it for this means that when it's not writing values, it's reading the sprite registers and it's accessing the sprite registers. And there's a little bit of bus direction logic here, so that I can say, for example, write a value from the external data bus or read a value to the internal data bus here. And what happens is that this logic down here is all to do with managing the internal sprite state. So based on the 6 megahertz clock, the sprite state gets advanced here, and then we can see here that it has a signal for load palette, load sprite size y, load sprite x, load sprite extent x, load scale y inverse, load scale x inverse, and load frame. These states here are synonymous with the states in the Java code for all of these states that we just talked about, the drawing sprite state. And this counter, because it counts up, and it goes into this demultiplexer thing here. So each one of these turn on and off in isolation. And the logic is reset by the beginning of the scanline. The beginning of the scanline is detected with this little flip-flop arrangement here. It's reset on hsync. The positive edge on hsync. Hsync causes this to read the value, and then the value for line start. Line start is held low at the beginning of the line and then goes high, for example. On the beginning of line start, it latches the current line B into a latch because we want to maintain a consistent Y position, if you like, based on that particular point. However, later on through the video hardware scanline, the Y position does change, so this is why we latch it. Anyway, so using the information from the sprite state plus the internal sprite register value, which is again reset to be 0 on the logic reset line, which is basically either sprite enable or the line start. This sprite index is reset to 0. And if the sprite height test fails, in other words, it early outs the sprite rejection. It early outs the sprite rejection test, basically. Or we have finished stamping pixels from the sprite to the scanline, then this triggers the sprite index to be incremented, and this sprite index is used to form part of the address that we're reading from for the sprite register RAM. So anyway, going back to the logic here, we have a whole bunch of latches here, which basically latch the internal values. So we latch the part, we latch the sprite Y, we latch the size Y, we latch the sprite X, so on and so forth. Latch the extent X, the Y inverse, the X inverse scale. Oh, some thunder has just started outside. And this is the early out sprite Y height check. So it takes the calculated inside height, and it just does basically a check. And then the signal down here tells you whether or not the sprite height test has failed and whether or not to trigger an early out. The inside height, of course, basically the height in terms of pixels in what would be inside the sprite is here, which takes the current line Y position and the what has been inverted sprite, and it adds them together, which is the same as what we saw in the Java code down here with the sprite Y test. Don't forget that this is inverted Y so that it does a subtraction rather than an add. And here is the lookup table. So this Java code, where it does the current sprite Y pixel inside the sprite data, this multiply just turns in to the 8 bits here plus the 8 bits here, turns it into a lookup table. Now this lookup table is just generated by some C code and then spat out. That's the binary file, and then the binary file is just loaded in here. It just basically does the calculation here, using the two 8-bit inputs and generating an 8-bit output, which is here the Y position of the sprite data, and actually includes all the shift and everything like that, so I don't need to worry about shift. This logic here takes the calculated sprite X pixel value and the calculated Y pixel value inside the sprite data. You can see here that it's selecting from the X position, it's selecting signal 5, 6, 7, 8, and 9. You would expect to see this because it's just basically shifting the value down by 5. It's dividing by 32. So, this signal selection here is a great example of how the hardware can very easily do the selection based on the shift value. And because the shift value is constant, then it doesn't need to jiggle about with all the signal values. Anyway, this does the flipping, so the flip X goes into the XORs and the flip Y goes into the XORs for the Y position, and all it does is do a bitwise conversion here. So this logic here handles the current sprite X pixel, but with the 5 bits of accuracy baked in. So at the beginning of the logic, what it does is that it reads the value, it latches the value in two 8-bit registers. Yeah, only two 8-bit registers, it's not too excessive. And the 16-bit value is basically read from what is being presented on the internal data bus, which in this case is basically half the X inverse value and then a bunch of zeros. But when it's actually stamping out pixels to the sprite data, it's reading the output from the add that it's doing. So what it's doing here is that it's taking the current sprite X pixel latch value and it's adding in the X scale inverse value, and it's doing a 16-bit add, and then it's presenting it as the next sprite X pixel value, which it latches, or it selects using this 2-to-1 selector here, and it selects the next X pixel, and then it latches it every single clock when it's meant to be doing that. Every single clock, it latches the next value, and so on and so forth. And then this sprite pixel value is then used in the logic here. So that basically covers the logic. The only part that really needs to be talked about after that is the current sprite X pixel coordinate range check. Again, we're doing the select with starting at signal 5, bit 5. So we're automatically doing the shift down already, and we've got a couple of comparators here cascaded, and we're looking for equal to or greater than. And we only want to do this test when this is high, basically, and we only want the pixel to be reached value to go low when greater than or equal to happens, and it's part of that state. So this little piece of logic here was needed because actually these two comparators, even though they are cascaded, I noticed that there was some settle time where occasionally it would say that it was equal to or greater than when it wasn't really equal to or greater than, and it would happen for a few nanoseconds. So I wanted to filter this out by having the test only done on the high of the sprite value inside the sprite sequence. The next sheet comprises the sprite memory data logic, which is down here, and two halves of the sprite Scanline logic, one for the odd Scanline and one for the even Scanline. That's why these two halves up here look like they're the same, and they practically are the same, apart from they're using different signals. And then there is the final pixel output selector logic here. So if we look at the sprite data logic first, we can see a very similar model where if the data is being written to the sprite scanline rams, which are here, 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 and here, then it selects the external memory address value, and if it's selecting the sprite data based on the sprite X position and sprite Y position, then it will select the relevant signals from those coordinates plus the sprite frame information into the address selection here, and then it uses the internal address selection plus some logic to select the actual RAM based on the external memory address. Then it reads all of the sprite data, and then it selects what sprite data RAM is actually presented to this internal sprite address based on the frame that comes in here. And because it's 4 bits per pixel, it only has 4 of these, and the corresponding outputs here. This means, of course, that all of these sprite RAMs are reading different values, and that's why they just get deselected here, or selected from here. Now, we'll only really look at one sprite scanline logic because it's an exact copy, just using different even or odd signals to activate the logic appropriately. So when the sprite scanline logic is outputting pixels, these are just simple counters which count up from 0 to 511 in decimal, 0 to 1FF in hex. And it just stamps out pixels to the output. It actually only counts up to 383, basically. And the sprite RAM, which is here, is just in output mode for the first half of the clock cycle, and it outputs the value, the pixel data, which is appropriately latched here, and then the appropriately latched pixel data is then selected by this pixel data selection logic here, depending on whether or not it wants to do the odd or even scanline. And then, for the other half of the clock cycle, it stamps out a clear value into the sprite RAM. Now, the eagle-eyed of you might notice that this is stamping with pull-ups. The bitwise value for 8 ones, which is binary value in decimal terms, it's 255. In hex, it's FF. And it's actually stamping out an inverted value, and that's because the value is coming through as an inverted value here, but it's also being read inverted from the RAM. So this is a non-inverted value, but internally in the RAM is held inverted. It's just done like this because the logic is a little bit simpler. The transparent pixel test, or the empty pixel test rather, as I suppose I should really call it, is done by this little logic here, which then feeds into whether or not it wants to select the incoming sprite data, or it wants to select, this is the incoming sprite data, or it wants to select the value that was previously written, or previously read from the sprite RAM. And that's the basic logic. Now, when it's going into rendering sprite data into the Scanline RAM, don't forget that the Scanline RAM has already been cleared. So what this does is that every time it has completed the reading of all of the sprite registers, and it's passed the Y height test. Then it goes into advancing the sprite X pixel coordinate in the Scanline RAM. And then every 6 MHz clock, it advances one more pixel until the sprite extent test turns this rendering logic off. And on this side, it's just the same logic, but inverted. So this is on do pixel here. This is on underscore do pixel. And they alternate between 0 and 1. So that when this one is outputting rendered pixels, this one is accepting rendered pixels, and vice versa. So what does it mean? So it means that using the debug view here, if I scroll it over to the right-hand side, what it means is that I can take the same data which is being used in the Java emulation, and I can take the same setup values here, all of these sprite values, I can just take them and I can put them into some test data, and I can inject that test data into the RAMs, and then I should get the same visible display on the simulated display. Here we go. It's taking ages because it's still rendering this view in the background here. And actually this is a lot slower than what it should be. But basically, if I go back to the simulation, you can see here that the simulation is gradually filling in the virtual simulated display. And this view in the simulation, hardware simulation, is the same as the view that we would expect to see from the Java emulation, which is great. It means that the hardware is working as expected. Now the test data has some test data here which stops the sprite output display here at this particular point on the display, and it re-enables it here. That's just for me to check that the sprite disable and re-enable logic works correctly. And then the next frame, there's none of that, and then it re-renders the next frame correctly. So this tells me that the hardware is working correctly. What it means now, of course, is that I've got emulation which matches the hardware, or rather the hardware matches the emulation. What it means is that I can do interesting stuff like this. So if I run this, this is a little test, and it just zooms in some scaled sprites with a logo. Now, because the emulation saves out the debug bus information, the hardware can actually take this information. So if I change the virtual data generator and I use the debug data output from what was just emulated, and then I start the simulation, it's compiling the netlist, but it does seem to be taking a little while longer. There we go. And the first frame is empty. And the next frame should, there you go, start displaying the logo. And then the next frame should start displaying the animation frames in the logo.